Hi everyone, my name is Chao Yen Chan, and my part is sampling. Sampling is the process of converting a continuous signal into discrete data points for computer analysis. And here is our result. We sample the ECG signals at a critical lag of 500 Hz. This is the most important parameter here. It means we are capturing 500 distinct data points every single second. And each vertical lines on this stem plot represents one of those samples. This process gives us the high resolution discrete signal needed for our next step convolution. Thank you.
The convolution process combines two signals to produce a third. At each step, we multiply overlapping points, sum them up, and store the results. This weighted average smooths the signal, emphasizing how slow trends while reducing frequency noise. Using the function once, we create a 10-point moving average filter. Each point in the window gets equal weight. This simple FIR filter acts as a low pass filter. The filter length in our code is n is equal to 10. Determine the balance between the noise reduction and the signal preservation. A longer window would smooth more but might over smooth some important features. After we define the filter using once function with order 10, we convolve the original signal with the filter impulse response using the conv function to obtain the filtered output.
Next, we'll discuss the DTFT, which is the discrete time Fourier transform. We use this to see the different frequencies inside our signal and to verify it if our filtering work. This top plot shows the signal before filtering and after filtering. The DTFT clearly reveals the low frequency ECG signal, but more importantly, it shows a sharp spikes at 50 and 60 Hz. This is the power line noise we need to remove. And now this plot showing that the after filtering, after our notch filters, as you can see, the noise at 50 and 60 Hz are completely gone. The DDFT proves that our filters work successfully, cleaning the signal while preserving the important ECG signal. This clean signal is now ready for convolution, and this DTFT is performed using the FFT function.
Hello, my name is Edison. I'll be explaining about the windowing method. So we already have the FIR filter. We just need to apply the windowing method by simply multiplying it. And then after that, we are here to export it into an audio file. So we can simply just convolute it with the original signal to get a clean signal after that.
Hello, I'm Yusuf. I'm going to present a bilinear transformation, which is an IIR filter design. First, we have m is equal to 3, which is the filter order. We also could find the omega c, the cutoff frequency. So by using these both, we could find the Butterworth equation. So we got the plot on the right. We can see the impulse response in numerator b and the denominator a. This shows the filter coefficient in time domain. Below that, we have the z-plane. It shows us the poles and zeros location. So we have 6 poles and 3 zeros. In this unit circle here, we could see that the system is stable.
Assalamu alaikum and hello everyone. Today I'll be presenting a quick overview of Z-plane analysis and how it helps us understand digital signal processing using MATLAB. So first we use the Z transform to convert a discrete time signal into the Z domain. This is useful because it lets us find a different equation of linear time invariant or LTI system, and it also helps us check if the system is stable and causal. So the formula for the forward Z transform is h of z equals the sum of h of n z powers of negative n, and the inverse Z transform brings the signal back to the time domain. So the key concept here is the region of convergence, which is the ROC. It tells us whether the system is stable. So if all the poles lie inside the unit circle in the Z-plane, the system is stable. If they fall outside, it's unstable. So let's talk about the MATLAB code. We use the first line, which creates a bandpass filter and gives us the numerator and denominator coefficients. Then we use the second part, which plots the poles and zeros in the output um, um, as shown in the circle below, and poles are x's. Um, if you look at the plot, you'll notice all the poles are inside the unit circle, which means the filter is stable. The symmetric shape also shows that the filter has real coefficients. So in summary, Z-plane analysis combined with MATLAB helps us design, test, and visualize digital filters efficiently.